Hello, my dear students. I hope all of you are doing well and more importantly, of course, learning, I believe. Uh, in this video today, what we will be learning will be about these three particular topics, that is like how to represent a vector, representation of a vector. We already did that in the first video. I hope you're keeping a track of that. If not, please go to that first video also where we have done types of vectors and some basic things. In this video also, we are going to be doing some of the basic things. Now, see, the introduction videos always are the most important videos, okay, because calculation, the exercises, anybody can do, but the concept will be always with the introduction videos that generally, okay, sometimes it's quite boring, but you have to know this, go through these introduction topics properly, okay. Then of course we will be learning about position vector, that is how do we represent a vector when it is in terms of, when the position of a particular vector with respect to the x-axis, y-axis and z-axis. So we're going to be learning something more about that. Then lastly, the most important topic would be direction cosines and direction ratios. Now especially this direction cosines, position vectors, direction ratios and all, we will be learning more in three-dimensional geometry also, but in this chapter also is going to be very important. So right from the word go, we will learn as much as possible. Okay, so some more basic things actually before we really jump into now the addition, the subtraction, the multiplication of vectors, dot product, cross product, and so on. Very simple topic, but okay. Let's not talk generally. Our main focus will be on the mathematical part only. So the conceptual part about the physics and all, let's keep it at bay now. Let's not think about that. How do we represent a vector? Representation of a vector we've already done, but okay, just a little bit more. What was a vector? A vector was a directed line segment. Okay, vector was a directed line segment where, say, if it's moving from A to B, A is called the initial point and B is called the final point, or also called as the terminal point. So a vector is a directed line segment moving from a particular direction. So as per this vector, it's from A to B. So how do you represent a vector? That can be represented in the form of vector AB. Okay, vector AB. So now this vector, if you write in terms of BA, then that would be wrong, because the vector is not starting from, the initial point is not B, the initial point is A, so it has to be AB. So this direction has to be really kept in mind, okay. It is very, very important, because AB will not be equal to BA for a particular vector. At the most, like AB, then if you want to represent it as BA, then most probably it has to be negative, because it has to be in the opposite direction. Then that's going to be, it has to be something like this, BA. Alright, so this is how we represent a vector. If a vector AB is directed from A to B, then we will be representing it by AB vector. Sometimes it is also denoted by single letters also, that is like maybe I can just write vector A also, but that's not a big concern. It depends, the names and all, it depends on us, isn't it? Then of course, like magnitude. So this AB is in terms of vector form. How do we find out its magnitude? Because as we had studied, what is a vector? A vector is a physical quantity which has this magnitude as well as direction. So direction already denoted here. Magnitude simply means, magnitude of a particular vector which is given to us here will be simply means like the length. Okay, length of the directed length of the directed line segment. Length of the directed line segment. Alright, and how do we really denote that? That will be simply modulus of vector AB. So if it's 5 centimeter magnitude, it will be just 5 centimeter. Alright, now why did I just decide to give you talk about this particular topic again was, see, some of the basic things I think I skipped in that first video, so just to brush up things more in details. Now, length of the directed line segment. So when I say length of the directed line segment, in that case I'm just talking of the magnitude only. So when you talk of the magnitude only, then it's about magnitude only, then it's a scalar, isn't it? It's a scalar quantity. So when I just talk of the length of the directed line segment or the magnitude of the vector, then we're talking of that scalar quantity. So magnitude of vector AB, which is called as modulus of AB, can also be simply written as length AB. Okay, so don't be confused sometimes when you come across this, because AB simply represents the length of the particular given vector. Bus. So that means once again, like if I have vector A, then its magnitude will be magnitude of modulus of vector A. That will also be written as simply A. So when I just say A and I mean to say it's about a vector, then in that case I mean to say that I'm talking about the what? Magnitude of a particular vector. Alright, I hope that's clear. Okay, alright. Now the next topic will be position vector of a given point. Position vector. Now for that, what I'll do is I will draw a three-dimensional space. Now imagination is very, very important, okay, in especially this three-dimensional space, vectors and all. Imagination holds the key. So because see, this is a board, this is a two-dimensional figure. Now I cannot show you the three-dimensional figure. At the most I can give you my imagination and then tell you to imagine, but if you're not ready for imagination, then that's really going to be difficult. Like उपाय नहीं, there's no other option. उपाय नहीं है, there's no other option. Imagination तो करना पड़ेगा. Okay, you have to imagine here, especially when you do vectors and three-dimensional space, because as I said, on a two-dimensional board we are going to imagine a three-dimensional space. So sometimes you might just think that no, this is really not working, but that is how it is. Because if you really see that in three-dimensional space, it is going to be correct. Okay, I will just imagine this as the x-axis. Alright, I will imagine this as the x-axis, this I will imagine as the y, and this as the z-axis. Now let us imagine a point in space. So that means like in space. So if there's a point in space, so that maybe I'll just draw here. Okay, so I'll imagine a point in space. Now let me just draw, let's say, let's draw a three-dimensional space with respect to x, y and z axis. So let me just imagine that this is my point x, y and z, the coordinate of this point. Alright, and then okay, I'll just rub this off and just bring it. Okay, करना तो पड़ेगा. I have to just draw it here only. Why नहीं है, but let's try to imagine. Okay, imagination. So now if we just imagine a three-dimensional space and then I have a point in the three-dimensional space. Now before that, in the last class we already discussed about unit vectors. Unit vectors, every vectors, they have their own unit vectors. How do we find out the unit vectors? The vector divided by its respective magnitude. Now it depends on the unit. You remember that, right? Now usually what happens is the x-axis, its unit vector is actually represented by I cap. That means when I say I cap, it's like a unit vector that is pointing in the direction of the x-axis. Okay, it's standard form. Y-axis, its unit vector is denoted by j, small letter j, j cap. And z-axis, its unit vector is denoted by k cap. Alright, actually I should be writing here, but I need that space here. Alright, now what do you mean by position? So this is a point in space with respect to x, y and z axis. Now so if a point is given to you in space, now how do you really represent that in the vector form with respect to the three axes, x, y and z axis? So what do you mean by position vector? You can just write down like a vector whose initial point is the origin. A vector whose initial point is the origin and final point is your given point, whatever be it. We are just talking in terms of general p, x, y, z. So the position vector of a given point is in other words like the position of a point in space with respect to x, y and z axis from the origin. Okay, from the origin. So In that case, like it's the position vector of this point P from the origin. So it will be OP vector. Alright, and how do we really denote this OP vector? If my coordinate, the coordinate of my point P is x, y and z, with respect to x-axis, y-axis and z-axis, it will be represented as like this: x I cap, every vector, no, every point in space, plus y j cap plus z k cap. So this is the way we will be actually representing the vector in space with respect to the three-dimensional space, that is x, y and z. So OP, so whenever we say position vector of a given point, always remember it is always with respect to the origin, the position of a point from the origin. That's called the position vector of a given point. And how do we represent that in space if it's x, y, z? So for example, if the point is, let's say, P minus 1, 2, 3, then how do we represent this OP vector? OP vector will be simply minus 1i plus 2j plus 3k cap. Alright, so that's how I'll be representing the position vector. In general, of course, OP vector, okay, is also represented as, in general, the general name that we give, single letter name, is also represented as vector R. Alright, so this is the general, the name, the representation that we give. How do we, the way we represent the position vector of a given point. And then similarly, if you want to find out its magnitude, if you want to find out the magnitude of the given vector, OP vector, that will be magnitude of the given vector, which will be OP, right? Magnitude, I told you, when we say magnitude, only the scalar quantity, or even like vector, magnitude of vector R or R. So many letters in which we can denote. It will be simply modulus, that is square root of x square plus y square plus z square. So this will give us the magnitude of the position vector of a particular given point. Are we done? Okay. Then the next important topic, I'll just rub this off once again. I will need a fresh diagram. You can also draw your diagram once again, because the next important topic will be direction cosines and direction, very important, direction ratios. So for that, of course, I'll need another three-dimensional space. So let us draw another three-dimensional space properly. Let's say like so let's say this is my x-axis, this is okay, this is my x-axis, this is my y-axis. You can name it in your own ways, okay, x, y and z, no hard and fast rule. So let's draw another point in space. Let's say this point. It's going to be okay. Sometimes it's kind of difficult, not difficult, but this is since we have to draw it in terms of our imagination, no? Let me just take this a little bit far away so that I need some more space for the point. Okay. Okay, I think that would be good enough. So let this be our point P, X, Y, and Z. Okay. Now, so what will be its position vector? Its position vector would be OP, but it is in space. Okay, so this point is somewhere here on the space, right? All right, outwards. So our position vector OP, which will be generally denoted by R in terms of magnitude. In terms of vector, it's going to be vector R. All right, that's clear. Okay. Now, the concept of direction cosines, very simple. Listen, very simple, okay? Don't complicate your mind. See, this position vector of this given point, what we see is that it is making an angle with respect to the x-axis, y-axis and z-axis, isn't it? Let's have a look. With respect to the x-axis, it is making this angle. Let us say that this angle is, let's say, alpha. Alright. With respect to the y-axis, this position vector is again making an angle. Let's say it is beta. With respect to the z-axis, it is making another angle. Let's say definitely, let's say it is gamma. So this point P, X, Y, Z, its position vector, it's definitely making an angle of alpha, beta and gamma with respect to the X, Y and Z axis respectively, isn't it? So what are these called? Actually, these are called direction angles. Alpha, beta and gamma, actually, okay, alpha, beta and gamma are called direction angles, just like direction coordinates, no? The angles, the angle which the point P makes with respect to x, y and z axis. So these are called the direction angles. Got it? What are direction cosines? Simply and the cosines of the direction, I'll just write D in short, and the cosines of the direction angles are called nothing but direction cosines. That means what are direction cosines? Cos alpha, cos beta and cos gamma. So these are called nothing but the direction cosines of a vector of a point P. So the cosines of the angles with a point P makes with respect to the x, y and z axis are simply called as the direction cosines. Cos alpha, cos beta and cos gamma. Very simple. Simple as that. Now, there are some relationships which we will have to understand. Now, how do we find, so let's say it's also denoted by L. L is actually cos of alpha, another way to denote. Now, if I have to find out this cos alpha, let me just rub the other parts for the time being. Now, remember this point P is in space. It might not look as it is, okay, but as I said, we have to imagine. Now, how do I find out? So let's say, suppose this is my point A. This is my point B and this is my point C. So now this point P, its coordinate is x, y and z with respect to the x-axis. That means this length is going to be x, this is going to be y, and this length is z. Right? About coordinate system, simple as that. Now if I just join, let's say this, if I just join OP, then actually in reality what will happen is it is going to look like a right angle, not look like, it is going to be a right angle triangle because this point P is in space here. And if I just join this OA, it is going to, because it's on the surface of a cube, okay, it's a cube. So it's going to be like, so it's going to be PAO, that is like PAO, where PA is going to be actually perpendicular to OA. So like if you're confused, like how is it possible? Like how is it possible? How can I say? No, because this is in space, as I said that I cannot show you exactly here. Something like, yes. See, for example, suppose this is a book. Okay, this is a book. So now what happens is, this is the x-axis, y-axis, z-axis, isn't it mutually perpendicular, right? The corners of a book. Now what happens is, for a point P that is lying here, let's say in space, what happens is, see this, if I just join this point, let's say if I just join this point, suppose this point. Now if this is my point, if I just join it with respect to this, then it's going to definitely be a right angle triangle. Similarly from this point, if I join to the edge, it's going to be a right angle triangle. So any point on space, definitely if I join it with respect to the origin, the axis, it is always going to give us a right angle triangle. Maybe this might also not be very accurate. It might not reach up to your imagination, but you can just have a look. One point P, join, you're going to get a right angle triangle. Here also, if I want point P join, you're going to get a right angle triangle. So this is more about our imagination only. I can see it, but like, okay, it's kind of difficult because this point P, that means like OA is going to be somewhere here, where OP is going to be like the hypotenuse. OA is going to be perpendicular to, you know, OA. This is going to be like perpendicular to OP. That means it's going to be somewhere here, perpendicular. Alright, so beyond that, of course, I can't do anything because this is more about imagination only. So it is a right angle triangle. We just have to know that, accept it. Okay, so this OA is X. What is OP? OP is R. So how do we find out cos alpha? Because alpha is the angle that is being made by the point P with respect to the x-axis. So how do we find out cos alpha? Cos alpha is like what? No, sorry. OP is the position vector. So how do we find out? That's going to be like base by hypotenuse. So that's like X by R. Okay, so that is how we find out the direction cosines, that is X by R. Similarly, M will be cos of beta, that is now with respect to triangle OP. I have to join this B now. Okay, so that is going to be, I'll just write Y by R. Similarly, N will be cos of gamma, that for that I have to join OP and C, so that is going to be Z by R. So this is how we find out the direction cosines. And don't forget, what is this R? R is actually nothing but the magnitude of the position vector of the given point. So that is actually what? X square plus Y square plus Z square. I mean the value of R. Alright, so that's how we really find out the direction cosines of a point X, Y, Z given to us in space. That is what we mean by direction cosines. Now there is a relationship between this direction cosines, and that relationship is given as L square plus M square plus N square equal to 1. Now in the NCERT textbook, its application is not, I haven't seen its application that much, but definitely this is well within the syllabus. So we are going to be needing these properties, okay, to solve further problems, maybe for competitive examinations and so on. So please take a note of this. Proof, of course, you can just prove it algebraically, you will get the proof. Alright? Okay. Okay, so you can try to get the proof, definitely you will get the proof. Algebraically also you can solve. Alright, now, so direction cosines is clear. Direction cosines is simply the cosines of the angle which is made by a point with respect to x, y and z axis. Now, next topic, that is direction ratios. Now, what are these direction ratios? These are nothing, these are just numbers. But like, what kind of numbers are they? Okay, what kind of numbers are they? They are special kind of numbers, and that will be, you can write down, that is like direction ratios are numbers. I'll just write in short, direction ratios are numbers. Direction ratios are numbers, generally denoted by, okay, generally it's denoted by A, B and C, generally denoted by A, B and C. Such that, actually what the rule is, such that they are proportional. That special kind of numbers, no, which are actually proportional to the direction cosine. So what are direction ratio? That's why it's called ratio. The concept of ratio is that only. No, these are just numbers, constant values, numbers. So certain special numbers which are actually proportional to the direction cosines. It is given as like such that, what I mean is like A by L will be equal to B by M. They are proportional. Should be equal to C by N. Let's say that all these values are equal to a constant value. Let's say K. So what are direction ratios? These are special kind of numbers, special numbers, not just any numbers, provided they fulfill the condition that they are directly proportional. I mean, they are proportional to their respective direction cosines. So all of them should be proportional to each other and should be equal to the same particular value, that is K, where of course K simply represents another constant value. Alright, and is that clear? Direction ratios. And then ultimately, what is the relationship between direction ratios and direction cosines? the relationship between direction ratios and direction cosines will be like direction cosines cos alpha is almost similar, will be given by A upon magnitude of the position vector of the given point. And what is that? A upon, where A represents the direction ratios. So with the help of direction ratios, you can find out the direction cosines also. And R will be, if the point P is x, y, z, so its magnitude will be x square plus root square root of x square plus y square plus z square. Similarly, cos of beta will be also B by magnitude of vector R. And then ultimately cos gamma will be equal to C by vector magnitude of vector R. So some of you may be just imagining, Anish, just now only you told us like cos alpha is x by y by z by, now again you have just changed to a, b, c, what you're doing whatever you want, or no, it's not like that. I'll tell you more about that. And that is, when you talk of a single coordinate, okay, when you talk of a single coordinate in space, let's say, maybe quickly, let's say this is one point P, x, y, and z. So when you talk of a single coordinate in space, what happens is its direction ratios A, B, and C for a single point, its direction ratios are same as the coordinates x, y, and z. That is only for when you have a vector with a single point, that is just one point itself, its position vector OP. So in that case, what happens is the direction ratios are same as the direction cosines x, y, and z. So that's going to be x square is also going to be a square plus b square plus c square. So similarly a square plus b square plus c square, a square plus b square plus c square, because for a single point it's the same concept, but we of course denote it by, yes, direction ratios. The general letters that we use is like a, b, and c. Alright, but when you have a vector like joining two points p and q, and then you're supposed to find out the direction ratios of not OP, not OQ, but about PQ, though in that case it's going to be quite different. It's not going to be representing the coordinates x, y, z of P or the other coordinate of Q. That of course we will learn, especially when we do three-dimensional geometry. There we will discuss more in detail about these direction ratios and direction cosines. Here, just the basic concepts that will be required for us for this particular chapter, because more in detail, I've seen that we do it in three-dimensional space, three-dimensional vectors only. Alright, so for now, just understand this, and then definitely when we do the exercises, it is really going to be more clear. This is just the concept that we're discussing. So yeah, a little bit of confusion might still remain, but it's alright, don't worry, we will learn together. Okay, so this were the basic introductions of vectors and how do we represent position vectors and so on. So I hope that next time onwards you can name any kind of vector. So in the next video we will be doing more about addition, subtraction, multiplication of vectors, and then we will move forward. Maybe just one or two more introduction class. After that we can straight away jump into the exercise and then proceed. Okay, so that's it for today, my dear students. Happy learning. If you've liked this video, please don't forget to subscribe, share, and yes, do hit the like button. Alright, so till then, see you in the next video with some more topics. Till then, take care.